All right, well, welcome everyone. On the webinar with me today is Frank Zigowitz, our telescope engineer, and Erica Wright, our community coordinator. Erica will be, and Frank will both be monitoring questions in the chat box while I talk. Roy couldn't be with us this evening, and our other team members, but they send their regards. Here's the overview. What we'll do, I want to start just by opening for a little Q&A from people, questions that might have come up while you were trying the ExoLab. But then we'll dive right into taking a look at what you did on the ExoLab for the star WASP 43 in some detail. And we'll look at some examples of other data sets from students from real classrooms, and take a look at the kinds of things, the kinds of data you can expect from a class. We'll kind of review in detail some of the features that may be hidden to you or that you haven't really fully found out about yet in both the modeling and telescope lab. We want to make sure we have lots of Q&A throughout. I should mention that on the call, on the webinar also, Jim, who just introduced himself in the chat box, is one of our mentor teachers. He's used ExoLab quite a bit, and can provide some insight in what's happened when his class used it. And Jackie Barge, also on the webinar, has used ExoLab in the past and has lots of insight from her own experience. And so I hope Jackie and Jim, you'll both bring your insights as we go along. So first of all, I'm just going to give a little wait time and see if anybody has any kind of burning questions from having done the data lab that you want to make sure I answer during this webinar. You can type those in the chat box or just ask them by unmuting yourself, since there's not too many of us on the webinar at the moment.
I had asked this question in the post that I did, but just like, it's the last calculation. No, the last calculation is the one that goes in the graph, but can you delete them, or are you just stuck with the last one that you did?
Yes. Jackie, as we go in detail, we're going to take a look at that data point of yours. It turns out that once you make a measurement, the lab currently does not allow you to delete a data point. Data is data. You can a priori decide that an image has some problems with it and decide not to measure a particular image for one reason or another. Either there's too many clouds, or you realize there's something wrong with it. We're going to take a look at your data point. You can remeasure a data point to try and get a better measurement if you think you might have done something wrong or missed something, and we're going to take a look at that. So, in fact, let's dive into the ExoLab right now. I'm going to bring it over from somewhere here. Where am I? Here I am, into view. Okay, so I am logged in as the teacher for our class here, the workshop teacher, and all of you have student accounts. Your teacher 1, teacher 2, teacher 3 are actually student accounts in my classroom account. So I want to take a look at the graph we've generated first, and I did a few points too, so we'll see that. Now, if I simply click graph brightness without telling the software what star I want it to look for the data in the database for, you'll see I get star blank on the night of undefined. someone noted on the forum that they had done work in school and then got home and tried to find their data and couldn't find it. And probably this is what happened. In order to see data that you did earlier, you need to, when you come to the ExoLab, once you leave the ExoLab and come back, the software doesn't know what star you want to look at. So you have to tell it by identifying the star in your list. So we are looking at the WASP 43, not this one, not from April 1st, but the one from March 28th. So I need to go further down my list and find it. And there, I'll just click on one of them. Now, as long as I'm not going to do any additional data reduction, I don't have to dark subtract. I can just select one of these images, hit graph brightness, and there's my data that I did. And you can use these to kind of bring it down into view and change the scale, as Roy went through last week. So there it is. Well, I'm not sure I see much of a pattern there. Maybe you do, but let's add the class graph. So this is all of your data. And suddenly, it looks like we may, in fact, have a light curve here, the evidence of a dip in brightness. I'm going to see if some of those on the lines, if I can get them, are they? Yeah, okay, so these two are a little low, and we have this one here, which, can I get that down? Looks like I can't, and I think this is the very point that Jackie was talking about at 1:30 a.m. And you can see here, I can actually see that this is teacher 11. So Jackie, I'm assuming you were teacher 11. And the relative bright, I see as I look at, yes, Jim, I see the brightness value on Jackie's measurement is 3.3 when all these other measurements are in this 1.13 to 1.20 range. So there's something peculiar going on here. And let's take a look at some of the tools to analyze the quality of the overall data set and what might be going on with this 1:30 a.m. point. So that's these tools over here, which are the components, which, as Rory described last week, are the raw measurements for the target star and each of the two comparison stars and the average of the two dark sky measurements. So a few things you can see here, and in a little bit I'll give you some other data sets to compare this component graph with. You can see that it's important to have comparison stars because there's little slight variations through the night here. This actually is a relatively good night for this WASP 43 data set, and one of the signals of that is the signal to noise. So the signal of the target star is up here in the 4500s, and the noise of the dark night sky background is down here below 2000. So we have, almost a 3-to-1 signal to noise ratio here. Few other things to notice as we look at this components and go back to our class graph is you notice the class graph shows a definite dip, but towards the end of our data set here, there's quite a lot of scatter. It starts getting very scattered. So let's go back and look at those components. And you could see some things happening at the end of our data run. You see that the dark sky background is getting brighter, kind of starting at, 12:45 or so. And this comparison star number 2 here is also getting a little bit brighter, certainly much more so than either of the target star or the other comparison star. So there's some strange things happening at the end where the ratio, which is really what you're measuring, the brightness ratio of the target star versus these comparison stars, is changing. And if we look at the altitude, actually, I didn't mean to look at the altitude yet. I gave it away. But anyway, so don't do this with your students. I wanted you to make a prediction as to what do you think is happening towards the end of our data set here. And of course, one of the things that's happening is the star is getting quite low in the sky, so the telescope is looking through lots of measurements, lots of atmosphere, and right, atmosphere on the Earth, and while students might think, well, all that haze in the atmosphere, wouldn't that make the dark sky measurement darker? That haze and atmosphere actually scatter a lot of light, so it makes the night sky background actually brighter, and introduces that noise that you see at the end of the class graph. So generally a good quality data set, a very defined dip here, but we have some definite scatter at the end. And then we have this issue of Jackie's 3.3. So let's go look at these components. Jim, so you can see why the sky would be brighter, but why is this star brighter? It's actually I have to look at. It's a great question. I have to look into detail. I mean, the differential is, of course, this star is either redder or bluer, and I have to think about this for a while. It scatters more blue.
It's redder, and we're also more red sensitive anyway.
So Frank is pointing out that the detector is more red sensitive, and the atmosphere scatters more blue light, and so we're particularly sensitive to red stars. So a redder star is going to end up brighter,
right?
Like the red sun,
setting sun,
like the setting sun.
Red.
Yeah. Okay. Okay.
Sorry,
Sorry, Frank is not on a microphone here, and I'm translating the interpretation here. But yeah, Jim, so this star, there's an effect of the color of the star that's happening in addition to the atmosphere. Now, Jackie's point here measured 3.3, and she says, I measured many times and the last two were 3.3. The first several times it was 1.2, the last two times it was 3.3. Here we actually did some detective work, Jackie, and we figured out what went wrong, and it's right here in the components. If you look at this 1:30 time slot, look right here. There's a teacher 11. I can't get that to come up for some reason here. Let me try it this way. There we go. Yeah, there's a teacher 11 red dot down here near the background sky at 1:30 a.m. And so we think what happened, Jackie, is that for your last two times, you ended up actually measuring the background sky when you thought you were measuring when you had your cursor, the cursor was still in the comparison star. And in fact, let's take a look at how that can happen. We'll go measure that star from 1:30 a.m. So I'm going to go back to analyze images, show my list. I want to subtract the dark first, so I'm going to find that dark somewhere here. I'm going to find a dark somewhere close to it. Okay. This was a question people asked. Could you, is it okay to use a dark image from a night that's not the same night as your data set? It is okay. Sometimes the dark images don't get taken. It's best to use a dark image from the same night. And as temperature changes in Arizona, it definitely affects that dark sky signal. So, but the place where you would generally find your dark sky images is at the bottom of your list of stars. And so let's see, at the bottom of this, and oddly, the WASP-43, the 328 darks ended up at the underneath the Cotter 2 data set from the night before. So sometimes you have to hunt around, but so let's choose the dark. And we're going to subtract that dark. We'll go back to the list and we're going to find that WASP-43 from 1:30 a.m. And of course, there's a 7-hour time difference. So that would be 8:30, 2017, 03/28 at 8:30 Universal Time. So here's the image, the culprit from Jackie's data set. And I'm going to go to page 9 to show you that this offers, page 9 offers a way to check with what your measurement is going to be even before you hit calculate and record. So this, as you'll recall, this is the target star, and these are the two component stars. So I'm going to measure once on the target star. Click in the comparison star box and measure once in the comparison star. Click. Did you see what I just did? I clicked on the next comparison star and moved on, but I hadn't changed where my cursor was. So let me go back and click on that comparison star 1, which is dimmer, it's 3,400. Then I have to click in the box and now click on that second comparison star. I have to click the dark sky box, find a dark sky piece near the target star. This was a question that came up from Scott in the forum. Is it better to make a measurement of the dark sky near your target star? And the answer is yes, because the sensitivity of our detector changes over the field of view. And in this lab, we haven't provided a calibration image to accommodate for that. Sometimes these are called flat field images that account for the way that the sensitivity of the detector changes. So you want to make your dark sky measurements near the target star. There's one.
And there could be some thin clouds.
Right.
That have variation across the field.
Yeah. Frank notes the second reason for making these measurements near the target star is if there's thin clouds that vary across the field of view. By keeping everything close, you minimize the scatter caused by that. So second measurement, and I kind of wiggle my cursor around till I get a relatively low number here in the 100s there, 2100s. All right, now, Jackie, at each step, I can check my work. So the calculation is we first average the comparison stars and average the night sky stars. We subtract in the night sky value, that 2000, from both the target star and the comparison star. And then the relative brightness is the ratio between the target star and that average of the comparison star, all dark subtracted. Now, I haven't clicked yet, so when I click, this is the relative brightness I should get. And notice, Jackie, it is 1.2, it's not 3.3. So something happened when you made your last couple of measurements, and we think we know what it is, which Frank really noticed this, which is, if we go back to the brightness, and now here's the, oh, actually, I think I just made one. What did I do? Where's mine? So, I don't know where. Oh, did I hit click on it? I thought I did, but anyway. All right. So Jackie, notice that your comparison star measures way down here at the same value as the background sky. So we think what happened is, when you were analyzing, the cursor was in the comparison star box, but you thought you had already moved down to the dark sky, and you clicked on a dark sky value. So you have to be careful what's going on there. But
we could make a 3.3.
yeah, so how would, right, so if we, I think if we click on a night sky here,
Yep.
and then we go here, there it is, right? So one of the comparison stars, if you missed and clicked on the night sky instead, you can see your relative brightness is in the 3.4s. Yes, great detective work. Speaking of Jim's nice discussion in the chat about uncertainty and the way different people are going to make measurements, I'd like to actually try that live right now. And this will only work for those of you who can have both the webinar window and the actual ExoLab window open at the same time. I'm hoping there's someone out there who can do this, because we're going to, what I want you to do is, along with me, at least one of you, hopefully Jim, you can do this, but maybe a couple other people online can do it as well. We're going to both measure the same image of a different data set. And this is something that is a good way to work with your students to see, to kind of have them get practice and see the variability that's just introduced by different people making the same measurement. So to do that, I'm going to show my list. And I'm actually going to, we're going to take a look at the Cotter 2 data set from 0404. She's up here. There it is. Actually, since I have an auto subtract from, it still thinks I'm on WASP 43, I'm going to refresh. I'm going to go up here and refresh the page. Sorry about that. So that I'm going to show my list, find that Cotter set, go to the bottom of it, find the dark, subtract the dark, show my list, and I'm going to go to the, actually, why don't we just go to the last image right above the dark there. So 1200, well, I'm sorry. Oh, no, yeah, let's not do that. Let's go to the first image. It's a little confusing. Sorry about that. So logged, yes, Jim, log in as teacher 16. Very good. And any of the others of you who have log in as your as the teacher, because that's my student accounts. So Jim, you and I are both going to measure this 070924 image. And the one thing I like about the Cotter 2 system is when you bring up the finder chart, there's this nice little parentheses of 3 stars that's easy to find on the image. And so here's the target, comparison 1, comparison 2. I'm gonna keep the finder chart on. You may not know that you don't have to take it off and find those stars. You can measure them right over the finder chart. So there's my target star. Here's my first comparison. I'm gonna go in a clockwise order. Here's my, oh good, Seth is doing it too as teacher 15, excellent. Here's my second. So, and here are 2 areas of night sky, kind of near the target star. Okay, and I'm gonna click, oops, see what I did? I don't have 2, I need another one. I didn't get that first one. And now I'm gonna click calculate and record. I got a relative brightness of 0.7033. So let's go graph. So there's my point, 1209, 703. Now, yes, Jim, Cotter 2. We're on the night of April 3rd. So that means universal time, April 4th. So you're looking for Cotter 2, 0404, the first image in the list, which is at 12:09 a.m. Okay. So, so Seth, you did yours. I'm going to reveal the class graph. Oh my, okay. So we have some people from the last webinar who did the same. Let's see, Seth, you are teacher 15. There's 5, 6, 9, 22, 20. Uh-oh, where are you, Seth, there? Am I seeing teacher 15? Huh. Wonder if I have to try again. Hide, show again. Not seeing it, but you do see these are all measurements. These measurements here are all of the same image by different people. And so that gives you a little bit of insight into the variability that's introduced through your measurement technique, through individual people's measurement technique. So you want to try to practice in a way, and sometimes some students will be way down here. I'm a little concerned that I don't see Seth's at all here for teacher 15. Jim, which teacher are you? 16. I'm not seeing teacher 16 either. Refresh. Let me try refreshing. Of course, that's going to get me completely 0 here. I'm going to have to, here. Right. So show my list. Let me go to Cotter 2. Let me graph. Let me show the class. Oh, there you are. Oh my, teacher 11. I'm not sure who teacher 11 is, but there's an issue here. And so this is the way, yeah, they have a, I can't, no, that's a 0.304. Yeah. Okay. And 5, 6, 9. Oh, there you are, 15 and 16. Seth, there you are, right here. Seth and Jim. So pretty close to each other. Jackie, that's you again, teacher 11. Well, let's go look at the components and see what happened. What time was that? 12 on? Ah, teacher 11. Look, there's a green dot where the background should be. So when you were measuring, right, the cursor was recording for the target star, but you clicked in an area that was near the background. Whoops, components, near the background. So, Jackie, the key thing is to really make sure, and I think the best thing is to be, when you're on Analyze Images on page 9. So, yeah, Jim, so right, each student can only have one value, but each class can have multiple values for the same image if you have multiple students making that measurement. Jackie, you can measure right over the finder chart. So again, let's show the technique. So I'm gonna first find the dark and subtract it. Subtract. Then I'm going to go to that first image in the list at the top of Cotter 2 here. It's 0709. It says, which of course is 1209 Arizona time. So I'm going to click on that. Bring up the finder chart, put it right over, and I don't have to move it. But I do have to make sure right now the target star window is highlighted over on the right. So I'm going to put my circle over the target star and click. Now I'm going to go over and highlight the comparison star. Put my circle over comparison star 1 and click. Highlight the next. Click. Highlight dark, click, highlight second dark, click. So you should get a 0.7, somewhere in the 0.7s, Jackie. And so we'll see. Class graph. I don't know. Maybe she fixed it.
Yes.
Yes! Yay! All right. Excellent. Woohoo! I like to see Jim's note in the chat box about a great discussion of uncertainty, which is always inherent in measurements of real data, and error, which you can minimize. Jim has a great discussion of this, and we'll be adding it to a teacher-created content section of the ExoLab community. A couple of people on the forum have asked for getting insights and some worksheets and things that teachers may use in using the ExoLab with their students. And so we're creating a whole section for teacher-created content, and Jim has a few things that we'll be loading up there. Great. So it looks like, and I think Jose has actually taken a bunch of data, and a couple of other teachers from this Cotter 2 data set. And it'd be great if you all wanted to try that for next week, because we'll be able to compare Cotter 2 and WASP 43 when we get to Data Lab. But you can start to see some things happening here. There's a little bit of something strange, why these are all down here. So we need more data. We'll have to take a look next week. Any questions about ImageLab right now? I want to show you some other data sets taken by students, not teachers, so you can see what you might expect. And let's see, where is that? I have, oh, sorry. All right. So here is some real data taken from a couple years ago, actually. And here are two class measurements of the same data set. This was measured by us here at the Center for Astrophysics. So you can see there's definitely scatter in this data set. This was measured by a classroom and much more scattered and much less conclusive. But you could see why if we look at the component and altitude graphs for this classroom. First of all, there's some gaps in their data here where they have no measurements. And one of those gaps happens to be right during the time when the transit was happening. So, so you want to make sure that your students' measurements cover the time period of the whole transit. And the other thing is we can see there's a lot of student measurements that are way up at the top and way at the bottom, potentially indicating some of the same things that Jackie had done. But actually, if we look right here, we can see these dots that are not in line with all the other components indicate that students have actually measured the wrong star in their measurement, and that's what these outliers are. So you can really use the component and altitude. You can also see that the beginning here of this data set is really low in the sky, really low in the sky. So there is a lot of, so there's both error by the students and uncertainty, or, well, actually, I don't know whether this is error or uncertainty, right? Because you know you're taking it through the atmosphere. Scatter.
These lines, the signal to noise is tighter here, less.
Right. So Frank is pointing out that you can also see, looking here, that through the night, the signal to noise at the beginning of the data set is small, and the signal to noise at the end is much better. So lots of different ways to analyze the quality of your data. Here's another screenshot of a class here, which is, so here is an example of what can happen if you set your students off to do the image lab and you haven't had an interaction with them to kind of test, you haven't had an interactive discussion with them to test if they know how to choose the right target star and component stars. So in this light curve, most of the measurements are actually outliers. And here's the component screenshot for this particular data set. So you can see that all these students were completely, I don't know what stars they were measuring. They were just measuring stars. And so, and so weren't really able to get a very good light curve here at all. Let's see, do I have any other screenshots of real students? Oh, here is another one. Actually, let's get rid of these. Here is a data set where you can see very, very definite dip in this data. It's got this strange thing going on at the end where it's going way up. Let's take a look at the components for that. Here are the components. And so again, you see a couple things happening. Signal to noise at the beginning is much better than signal to noise at the end, right? You see at the end, the night sky is getting brighter. the two comparison stars that were kind of most of the night separated in brightness suddenly become similar in brightness, indicating they might actually be different colors. And the target star getting dimmer as well in the same way. So let's take a look at the altitude. All right. So again, starting here just before midnight, we're really getting low in the sky. And so these points over here are really from this area towards the end of the data run. Jackie, I will try to, that's a great idea. I'm going to try and make another folder of student examples and kind of case studies, and we'll put those on the educator community as well.
And there are one or two guides.
Yeah, so there are some examples in the PDF guides. And the other thing to realize is that within the image lab, if we're here in graph brightness, on page 5, there actually is this field guide to messy data identifying the different factors. So you kind of rotate this cube, and here is an example of where moonlight affects the data of TRES 5. So there's TRES 5 on one night, another night where it's kind of funny here, and another night where it was a full moon and it's very messy. So here's an example of the moon was up and then it was setting on that first data set. So it was scattered and then got better. That's for this one. The moon was up and then went down. Actually, let's see, which one is that for? Oh yeah. So I'm sorry. Anyway, you can take a look and compare. So here's another effect of the horizon. Whoops, let me get that. And here's the example of Cotter 2. Again, I think this is the one I just showed you, where the signal to noise not so good at the beginning, better at the end. Altitude low at the beginning.
And to point that out, the student's question, as we talked about that.
Jim is asking, is there a general rule for altitude limits? Only use images higher than 45 degrees? That's being too meticulous, because it's very hard to get a whole data set that's above 45 degrees. I think you still want to use the images. You just want to be aware of the altitude. Starting at 30 degrees, the amount of air mass that is distorting the light starts to really increase. And really, once you get 25 or 20 degrees, we typically don't even take data for an object that's going to be that low.
Unless that's the only one for the night.
Right, unless it's the only one for the night. And so, anyway, great. Okay, so that's the image lab in detail. I did say I wanted to try and cover some details of the modeling lab and telescope lab that are good to know for teachers. Roy went over them briefly in last week's webinar, but I wanted to kind of point out that the three things that the modeling lab, three really important variables the modeling lab allows students to experiment with are planet size, right? Planet speed of orbit, although again, every model represents some things well and misrepresents others. And in this model, you can change the speed on the visualization, but of course in real space, orbits only get faster because the actual distance to the star changes. And then the orbital tilt. So those are the three things that can be adjusted. The modeling lab asks students to actually drag and make a prediction for when they'll see a dip. And while students can almost universally do this qualitatively, they have a really hard time with the idea of predicting, here's a star, here's a planet that's 0.2, 1/5 the size, the diameter of its star. If we were to double the diameter of this planet, what do you think most students would predict would happen to the dip of that planet? And we can use page 5 of the modeling lab to actually, rather than have students can make a prediction, but then they can, I'll see if I can get this to go faster. But then I can click simulate, and now the computer itself is reading out the measurements that you would get with a star that size. And so we just did the default model size, which is 0.2 times the width of its star. And now I'm going to, as it comes in front, start over. Stop, wait. Oh, come back around. All right, well, sorry. I'm on. There we go. All right, so we'll wait for that big star. So over here on the left, we have 0.2 times the size of its star. And now we're going to get the simulation of what would happen to a planet double the diameter. Most students would say that the dip will be double the depth. So from 4% to 8%. But in fact, the dip is proportional to the area blocked by the planet, and the area goes as the square of the diameter. So twice as big, 4 times the depth. And that's a quantitative interpretation that a lot of students have a lot of trouble with. And so we'll also post, there's a great resource called Transit Math, created by a NASA scientist and educator, Sten Oldenwald, that I will put in a folder of NASA resources on the ExoLab, which has lots of problems, kind of math exercises for kids to get used to that quantitative idea that the dip in the transit curve is related to the area covered up by the planet. And so there's a square or a square root depending on which direction you're going, and we'll see in the data lab next week that we have to take the square root of the depth of the data to figure out the size of the planet. Exactly, yeah. Okay, that's modeling lab. On telescope lab, I want to, Mita had asked, can you find out if the moon is going to be up? And here, in fact, tonight we have WASP 43 in the constellation Sextans. And it's taken between the hours of 8 and midnight in Arizona. And we're going to take that image. But you can actually use the telescope interface to find out if you want to look back, and let's look back at a data set or forward and see if there was a full moon, or where your target star was in the sky. I'm going to actually go a little bit later here. So there, right here is WASP 43. So we're here at 6:25 tonight, and WASP 43 is a target. And as we get a little later, you'll see it's getting higher in the sky. And whoops, sorry. Whoa. And so you can kind of see how high in the sky it is. And you can also see that indeed there is a waning, a waxing gibbous moon tonight that may affect the data set of WASP 43, which is, where to go? I've lost it, but it's down here near Leo. Oh, so it's a little tricky to work the telescope interface, but if you practice, you'll get used to figuring out how to explore the sky. Okay. One other question that I wanted to go over before we start wrapping up here, I think. Student samples, modeling, and telescope lab. Oh, a question on the forum asked about, are there any resources for finding out about the target stars in the ExoLab? And in fact, I just, you asked, and so we created a resource just for that. I put it in, Scott, in the forum, I put a link to it. We will add this link again to both to the ExoLab educators community in a special section for information about the target stars. Jackie, you had asked earlier for kind of a highlights of weird and wonderful exoplanets, and we're trying to create that for you as well. So, in a section of information about the stars. So you can say, Scott asked, is there a quick way to find information about the star that that we're going to study? And so we actually created a page here. And Jim, don't get ahead of us, because in fact, this page that we created links to the page that you just typed in the chat box. So for WASP 43, we find WASP 43 on this page. You can click on two things. If you click on the image, what comes up is a 3D visualization from NASA's exoplanet exploration group of the target star. So here's WASP 43, and you can, move it around, and you can zoom in and out, and you can compare it to Jupiter. So you can see that it is Jupiter size. Now you may not want to do this before students collect their own data about WASP 43. That's definitely a pedagogical question, whether you want them to know too much information about their star before they themselves determine the parameters of the star. This you can also look at the system of WASP 43 and compare it to our solar system in this which you can see, WASP-43. Here's the orbit of Mercury, and here's the orbit of WASP-43. It is way close to its star. So very close. So that's what you get if you click on the image of a star. If you click on this link, you'll get to the actual professional database of data about that star. And that's the link Jim has given, which, so WASP-43, and here's information about its period. So it goes around its star. Its year is actually 0.8 days, so it's very close to its star. Gives you information about the depth of the transit, which here is 2.5%. And again, you may not want to introduce all this information to your students before they determine their own results, but it's a great thing to show them after they examine their own data. Okay. Let's see. Are there other? Is there other questions during the week? I'm going to get back to my slides here. Okay. So next steps are for you guys to keep working in the ExoLab to see how it works. It would be great if you would use your teacher accounts, if you have the time, to try the Cotter 2 from 0404 data set, because next week we're going to take a look at the data lab, and it'll be really nice to be able to compare the Cotter 2 with the WASP-43 within the data lab, and we'll be looking at that in the in detail. So we're thrilled to have all of you asking questions and asking for particular resources that you need, because you're all helping us make the ExoLab more accessible and more relevant and more useful for teachers. Yeah, Jackie, that's a great question. If you do Cotter 2, you can use the same time assignments that Erica gave you for WASP-43. If you find there's some times missing when you look at the class data and you want to do those to fill in, that would be great too. So just to remind you, over the next now 3 weeks, next week we'll be looking at the data lab in detail and learning how to publish your class data to our community database, so that their work is actually being both added to all the data we've collected on that particular star, and kind of becomes a part of the larger ExoLab search community. April 19th, we have one of our grad students here at the CFA, Shani Nava, who is using spectroscopy to study the atmospheres of exoplanets. She's going to do a presentation about her work, and so you don't want to miss that. And then April 26th, we'll really focus on tips and tricks from teachers who've used the site. One final thing to call your attention to in the ExoLab community. We will also, this week, in addition to mentor teachers, we have an amateur astronomer who's been using MicroObservatory. His name's Martin Fowler. He introduced himself, but he also made a post. He's been doing some more complicated analysis of the same microobservatory images that we look at in ExoLab, and he made a post of how he did it for the WASP-43 data set that we just did. So he downloads all 93 images from the MicroObservatory database. He uploads them into a specialized software that astronomers doing photometry use. And he shows the difference between the specialized software results and our ExoLab results. And then he shows a process of smoothing the data by taking three image averages. And you can see that really starts to make the WASP-43 light curve stand out much more than it does in our kind of more raw light curve up here. And he's actually been entering our MicroObservatory data into the Exoplanet Transit Database, which is a Czechoslovakian Astronomical Society website. And they have a data modeling tool that is more complicated than the Data Lab modeling tool that we're going to look at next week. So Martin will be available for questions both online and in some of these webinars. I encourage you to take a look at that if you're interested. That's getting kind of a little deep in the weeds for some. So, but we just wanted to show that there is a lot of depth to using the ExoLab. I think that is the conclusion of what we have for today's webinar. If anyone has any late-breaking questions, we'll take them. Otherwise, we'll end the meeting. Jim, does that averaging change the slope of the transiting? Yeah, let's take a look at that. Yeah, so you could see the WASP-43 data. You'll remember it was the altitude only really went down. It was kind of flat in the sky, and it only really went down towards the end of the night. So you kind of get this tailing up and a slight slope increased. The modeling tool in the Czech site has a trend, a detrending tool that resets the slope to flat. So that's what changes the slope rather than, I think, the averaging. Great question. Okay. You guys have been great. We'll make sure some of Jim's resources are actually posted to the Data Lab, so you can, or to the ExoLab community, so you can get them. And we look forward to continuing the discussion online, and keep the questions coming. Thanks, everyone.